Chapter 13. In this chapter, we'll see how we can calculate radiation exchange between different surfaces. And for that, we need to define something called as a view factor, which is a fraction of radiation leaving surface I that is intercepted by surface J. Now, what does this mean? So let's say we have two surfaces, surface I, which is the blue surface here, and surface J, which is the orange surface here. Now, because of its temperature, surface I will emit radiation in all directions. It will, because it's a diffuse surface, it will emit equal amount of radiation in all directions. But as you see here, not all radiation will be intercepted by this particular surface J. Only some part of the radiation will be intercepted by Tj, and we need to calculate how much of the radiation emitted by Ti is intercepted by Tj. And for that, we define something called as a view factor. Now, what view factor tells us is that how much of uh, surface Tj is viewed from surface Ti. Okay, so if this was surface Ti, how much of it is viewed from surface uh, Ti, and the amount of radiation that is intercepted will be proportional to that fraction. Okay, so it's usually represented by f of I comma j. So your view factor is usually defined by a uppercase F, and in subscripts you will have Ij, where I is your surface from which radiation is emitted and J is the surface which intercepts the radiation. So if you see a notation Fij, it will mean that the radiation is leaving I and is intercepted or is falling on J. And this particular case here is a simple case, but you may have different scenarios where you might have to calculate how much heat is being, or how much radiation heat flux is being exchanged between two surfaces. So that's why um, finding the view factor in that particular system or in different scenarios is extremely important. So for finding this view factor, what we do is we have a bunch of rules that view factor follows, which makes us easier to calculate the view factor. And you'll see that when we look at an example in just a bit. So the first rule that is followed is a reciprocity relation. So what does reciprocity relation mean? It means that your AI into f of ij, that means your area of surface I multiplied by f of ij equals to area of surface j multiplied by f of ji. That means um, your the area of I multiplied by the view factor of how I views j is equal to area of j multiplied by how j views I. Okay, so this here is a very important relation that we will be using often. So you always have to keep this in mind. The next rule that we will use is the summation rule. So what the summation rule says is that if you have a system of surfaces, or if you have multiple surfaces on which are intercepting a radiation from a particular surface I, the summation of the view factors will be equal to 1. Now what does that mean? So let's say you have a square which has 4 surfaces. So and let's say these surfaces are the inner surface of the square. So this right here is surface 1, surface 2, surface 3, and surface 4. Now let's assume that surface 1 is emitting radiation in all directions. Okay, So um, the view factor of surface 1 to 2 is, say, f of 1 2. The view factor of surface 1 to 3 is f of 1 3, and view factor from surface 1 to 4 is 1 4. And in this case, surface 1 won't view itself, but we will just write it down in case we have a complex, or we have a concave surface. So in that case, your surface will view itself as well. So if you see, all the radiation that is emitted by surface 1 is either intercepted by 2, 3 or 4, and it does not leave this enclosed surface enclosed enclosure. So whatever radiation is emitted is intercepted by surface 1 2 3 and 4, which means that your f of 1 1 plus f of 1 2 plus f of 1 3 plus f of 1 4 is equal to 1. And that's what this means. That's what the summation means. So in this case, your I is 1 and your j will go from 1 to 4. So you will have f of 1 1 1 2 1 3 and 1 4. Now for plane surfaces or convex surfaces, and by convex I mean if you have a surface something like this, okay, and the outer surface is your surface of interest or surface that is emitting radiation, the convex surface won't view itself, but in a concave surface you will have a view factor, non-zero view factor. So if you have a plane surface or a convex surface, your f of ii equals will be equal to f of jj will be equal to 0. That means f of 1 1 equals to 0, because there is no way in which surface 1 is able to view itself. Now let's say you have n enclosures or n surfaces. So in that case you will need a total of n square view factors. Let's see how. So let's take the example of the square enclosure again, and because it's square all the areas will be equal. So the number of view factors that we will need to find the exchange of radiation within all the surfaces. So your equation 1 is telling you how much radiation released or emitted from 1 is intercepted by 1 2 3 and 4. Similarly, 2 tells us how much radiation from 2. Now your I is 2 and j is moving from 1 to 4. So how much radiation from 2 is intercepted by 1 2 3 and 4. In the next equation, how much radiation emitted from 3 is intercepted by 1 2 3 and 4. So that's why you have f31 f32 f33 and f34. And in the fourth one you have how much radiation emitted from 4 is intercepted by the other three surfaces. In this case you have all the FIIs or FJJs in as diagonal terms. So you have F11, F22, F33 and F44 as diagonal terms. But you in all, like, you need not have to directly calculate all the view factors. You can use the two rules that we just defined, that's the reciprocity and the summation rule, and also the fact that for plane and convex surfaces, your view factors are your view factors of surface viewing itself will be 0. So let's see if when we apply reciprocity and summation rule, what our view factors will be. Okay, so we sorry, we use the relation Fii equals to 0, and reciprocity that A of Fij equals to Aj of Fji, and the summation rule. So because we have a square, our Fi, our Ai will be equal to Aj. Okay, so doing that, for our first equation, our f11 is 0, our f12 is f12, f13 is f13, but for f4, so for equation 1, we can write our summation rule as f11 plus f12 plus f13 plus f14 equals to 0, which will give us, now because this here is 0, it will give us f14 equals to 1. Oh, so this has to be 1 and not 0. Equal to 1 will give us 1 minus f13, or let me just write it that like this way, minus f12. Okay, so I've substituted f14 as 1 minus f13 minus f12 right here. Similarly, for your second set of view factors, we can write f21, which is right here as f12 by reciprocity. So your a1 times f12 will be equal to a2 times f21, and because a1 is equal to a2, we can say that f12 is equal to f21. So I have used this relation, and this is after assuming a1 equals to a2. These areas will cancel out. Okay, so in the second set of view factors, I have used f12 instead of f21. uh, we don't have any relation for f23 yet, so f23 will remain f23, f22 will be 0, and again f24 can be written using reciprocity and the summation rule. So the summation of f12 f23 plus f24 will be equal to 1, and similarly your f24 will be 1 minus f23 minus f12. So I've directly written that instead of f24. For our next set of equation, I have replaced f31 by f13 by using reciprocity. So again, this it's similar to what we did for f12 and f21. Because our areas are equal, f31 will be equal to f13, and for f32 I've done the same thing. So instead of f32, by reciprocity I've written it as f23. f33 will be 0, and by summation rule I get f34 as 1 minus f13 minus f23, and I've written that here. Now for f14 by reciprocity, so your by reciprocity your f14 will be equal to f41, your f24 will be equal to f42, your uh, 34 will be equal to f43. So f14 is this term right here, f23 is this term right here, and f34 is this term right here. So I have replaced them in the last set of equations, and your f44 will be 0. Okay, so what this means is that instead of calculating 4 into 4 16 view factors, now we just have to calculate for f12, f13, f23, and we can find the remaining view factors just by the other relations that we have. Okay, so we just need to calculate we just need to calculate F12, F13 and F23. So we just have to calculate 3 view factors instead of 16. Okay, so that's why these equations are extremely important. Okay, so let's look at a different example. So let's say we have two spheres. One sphere, the small sphere is enclosed in inside a large sphere, and the surface of interest is the outer surface of the inner sphere and the inner surface of the outer sphere. So the radiation or the radiosity from the inner surface, so the outer surface of the inner sphere or sphere 1 is J1, and the radiosity from sphere 2 is J2. Okay, so we use reciprocity, and by reciprocity we get A of 1 into F of 1 2 equals to A2 into F of 2 1. By summation rule we have F of 1 2 plus F of 1 1 equal to 1, and F of 2 1 plus F of 2 2 equals to 2. Now keep in mind that F of 1 1 will be 0 because this is a convex surface and there is no way in which radiation emitted from 1 will land on 1 again. So but it is not true for F of 2 because the radiation emitted from surface 2 will land on surface 1. So the radiation will land on surface 1. Sorry, radiation from 2 will land on surface 2 again. So this is a non-zero quantity and we can see that. So your F of 2 2 from summation rule can be written as F of, so this will be F of 2 2 equals to 1 minus F of 2 1. Okay, and uh, your F of 1 2 is 1, so we can replace that in this equation right here. So A1 into 1 equals to A2 into F of 2 1, or we get F of 2 1 as A1 by A2. Okay, and I will replace that in this equation right here, which will give me F of 2 2 equals to 1 minus A1 by A2, which is a non-zero quantity. We know the, and we can calculate the areas of A1 and A2. Okay, so okay, so this is how you can calculate the view factors in geometries that are like not square, so or which have like concave and convex surfaces. So now we've calculated, so if you're given the diameters of these two spheres, you can easily calculate what the view factor is for F of 2 2, and then you'll be able to calculate the net radiation exchange. Now what is the equation by which you can calculate the net radiation exchange? Okay, so let's look at how much heat transfer takes place between 1 and 2, sorry, I and j. So Qij will be equal to the heat transferred from I to j minus the heat transferred from j to I. So this is nothing but saying a q out minus qn, and that will be the net radiation exchange. So in our case, our Q12 will be the amount of radiation going from 1 to 2, or the radiation exchange between 1 to 2 minus radiation exchange between 2 to 1. So this can be written as Q of ij equals to AI into F of ij into your emissive power or your emission from a body I minus aj into f of ji into the emission or radiation emitted by body j. Okay, and this will be nothing but, so when you take this you can and if your areas are equal, you can take, if ai is equal to aj, you can take ai common, and by reciprocity your f of ij will be equal to f of ji, f of ji. So your equation will be q of ij equals to ai into f of ij into the Stephen Boltzmann constant sigma times ti to the power 4 minus tj to the power 4. Okay, that's when we substitute ei equals to sigma times ti to the power 4, and this will be sigma times tj to the power 4. That's the emissive power of each of these surfaces. Now, your textbook gives you the view factors in some of the for some of the cases, or for some of the geometries. So I would encourage you to go to table 13.1 and look at the relations given for different sets of geometries. So the first relation that they've given is for parallel plates with middle connected by a perpendicular. That means these two plates are exactly parallel and their centers are aligned. So the center of surface I is aligned with center of surface J, and they've given us the width of the two plates or the two surfaces I and J, and we know what is the distance between the two plates. So in this particular scenario, the view factor of ij will be this particular equation here. So it will be under root of w uppercase wi plus wj whole square plus 4 minus wj minus I whole square plus 4, and the under root of that divided by 2 times wi, and they've defined the uppercase wi as the length of the surfaces divided by the distance between the two surfaces. Okay, so if you get a scenario which resembles this particular case, you can directly use this equation here to calculate your view factors. Okay, but in case of this scenario where you have two equal plates but they are uh, at an angle from each other, so these plates are still parallel, and by parallel they mean that they run infinitely into the page or outside the page. So they are infinitely long plates, but uh, they are at an angle alpha from each other. So in this case your view factor f of ij will be equal to 1 minus sine of alpha by 2, and let's see what we get if we have alpha equals to say 90 degrees. So if you have alpha equals to 90 degrees, your sine of alpha by 2 will be sine of 45, and in that case your sine of 45 is 1 over root 2. So your f of ij will be 1 minus 1 over root 2. Okay, so similarly if you have completely parallel plates, so if your alpha is 0, that means your surface I and surface J will completely coincide each other. In that case your alpha will be 0 and you'll be left with f of ij equals to 1. That means your I surface will completely view J surface and your J surface will completely view I surface, which will be true if those two surfaces coincide each other. Similarly, they've given you relations for some other scenarios as well. You have a scenario for an enclosure where you have three surfaces enclosed in the shape of a triangle, and that's the view factor for that. So we will be using these relations in a solved example, and also in our also in some of the problems that we do. So make sure that you go to table 13.1 and go through these view factors once. And remember that these view factors in table 13.1 were for a 2D scenario. For a 3D scenario, they've given you a different set of view factors, and which is given in table 13.2. You have a scenario where you have two plates which resemble opposite surface of a rectangle, and the view factor for that is given right here. You can have two coaxial parallel discs, and the view factor for that is given right here. And you can have two rectangular plates that are perpendicular to each other, and again you have the relation for view factor given right here. These view factors are a bit complicated, but if in some scenarios these equations reduce down to some simple forms, if you know the and you will be given all the dimensions, so you don't have to worry about this. And mostly in this course we will be looking at view factors for 2D geometries. So